So linear inequalities. If you know how to solve a linear equation, you already know how to solve a linear inequality. There's one minor thing we have to watch out for. So here I have a linear equation, I've got an equal sign, and next to it I have a linear inequality that looks basically the same, except where I have my equal sign, I have a greater than or equal to symbol. We know how to solve this. First thing you want to do is subtract 5 on this side so that it's gone from the left-hand side. Once that's simplified, we just divide both sides by 3 to get our final answer. I did the exact same thing here. To isolate for x, I have to bring that 5 over and subtract, get -9, and divide both sides by 3, and get x is greater than or equal to -3. So that says that so long as x is greater than or equal to -3, this inequality holds. This left-hand side will always be greater than or equal to -4. There's one minor thing you have to watch out for. We treat inequalities like equations, except if we divide both sides of the inequality by a negative number, or multiply both sides of an inequality by a negative number, the inequality symbol will swap directions. So here I have a greater than or equal to symbol. I want to get rid of this -7, and so I add it on the right-hand side, and now I have 12. Now I want to get rid of this -2, and the opposite of multiplying by -2 is, of course, dividing by -2. And because I'm dividing by a negative, from this step to this step, I've swapped the inequality symbol from a greater than or equal to a less than or equal to. So one small thing to look out for, otherwise treat it exactly like you would an equation. When we're dealing with inequalities, it's possible to get a double inequality. We can get some value of x between two values. Of course, that doesn't work for an equation. X can only be equal to one single thing at a time. But with inequalities, x can be in some range. So here I have -7 is less than -2x plus 1, which is less than -3. You can think of this as having 3 sections, and my goal is to get x alone in the middle. So if I want to get x alone, first thing I want to do is get rid of that plus 1, just like you would in an equation. We know that the opposite of adding 1 is subtracting 1. If I subtract 1 from each of my 3 sections, I'm left with -7 minus 1. Now it's gone from the middle section, and -3 minus 1. Now I've simplified. That becomes -8. That becomes -4. And once again, if I want to get rid of this -2 in front of the x, I've got to divide each of the sections by -2. And don't forget, because I'm dividing by a negative, the inequality symbols will swap direction, and we get this as our final answer. X is some number between 2 and 4. That says that as long as x is some number between 2 and 4, this initial inequality will hold. So for polynomial inequalities, unfortunately, it's not so straightforward. The easiest way to deal with a polynomial inequality is to think of it graphically. So say this is some function f of x, and I ask you, when is f of x greater than 0? That's another way of saying, when are your y values greater than 0? When is the graph in the positives? So if I look at this graph, in this entire section here, between 1 and 2, my graph is above the x-axis, which means my y-coordinates are positive. So we have one interval. F of x is greater than 0, or is positive, when x is between -1 and 2. Then my graph becomes negative for a bit, but after 3, it'll be positive again, on toward infinity. So we have another interval where f of x is positive when x is greater than 3. Alternately, if you're asked when is f of x negative or when is f of x less than 0, we're looking at the intervals on this graph when it's below the x-axis. So over here, when x is less than -1, that entire section, your graph will be below the x-axis. And in here, in this little bit, between 2 and 3, your graph is negative or or below the x-axis. So here's an algebraic solution. So say you factored this, and you got these 3 factors. If we were to solve, we know that the solutions to this are +4, -1, +3. So those are the zeros on my graph. -1, +3, and +4. Remember that this means that that is an order 2 0, so my graph is going to bounce at 3. And because of the negative in front, my graph is flipped over, and so the end behavior is pointing downward because this is an even degree polynomial, degree 4. So there's my end behavior, there are my zeros, there's the special 0 that bounces back. I have to figure out when this polynomial is less than or equal to 0. Well, when is it below the x-axis? Right here, when x is less than -1, and over here, when x is greater than 4. But you'll notice I also included the 0, 3. Because it has the equality symbol under here, you have to make sure to also include all of the zeros. So my final answer, when x is less than or equal to -1 in order to include the 0, when x is equal to 3 to include the 0, and finally when x is greater than or equal to 4, and again include the 0. So the reciprocal of a function is a function you get when you take some other known function and just flip it under 1, literally the reciprocal. What that does is it takes all of the y coordinates from your initial function and flips them over so that they're now 1 over y, right? The point 1, 2 would become 1 over 2. The point, let's say 5, 10 would be 5, 1 over 10, for example. If you know these properties of the initial function, we immediately know some properties of its reciprocal, which makes it simple to graph. First thing, if you know the zeros of your function, when you take the reciprocal of 0, well, that's not allowed, it's undefined. And for that reason, we get vertical asymptotes anywhere that your initial function had zeros. Anywhere your initial function is increasing, its reciprocal will be decreasing. The larger a number gets, the smaller its reciprocal is, right? The reciprocal of 2 is 1/2, of 10 is 1 over 10, 100, 1 over 100. The larger a number, the smaller its reciprocal. And vice versa. If a function is decreasing, its reciprocal will increase. This one is the one that doesn't change. Wherever your initial function is positive, it will remain positive. The reciprocal of a positive number is still a positive value, and the reciprocal of a negative number is still a negative number. Another useful trait, if your function has a maximum at the coordinates x, y, your reciprocal will have a minimum at the coordinates x, 1 over y. Once again, all the points flip over. Where your graph has a minimum, it will have a maximum. One last very important property, every single reciprocal function has a horizontal asymptote y equals to 0. That sort of makes sense. As x approaches very large values, your graph will be approaching very small values. We've already mentioned the reciprocal of very large numbers gets very small. The reciprocal of a number like 1,000 is 0.001. So we have two examples here. First up, the reciprocal of a line. So sketch this line and its reciprocal on the same axes. This is a line with slope 1 and y-intercept -3. So there's the y-intercept, over 1, up 1, over 1, up 1, etc. So we end up with a line with a y-intercept at -3, an x-intercept at 3, and that's always increasing. So going through the properties we've just discussed, zeros become vertical asymptotes. So where this line had an x-intercept or 0, the reciprocal, the blue graph, will have a vertical asymptote. This graph is always increasing, therefore the reciprocal is always decreasing. It's heading down as we move from left to right. Where this function is positive, the line, its reciprocal remained positive, right? Above the x-axis, above the x-axis. Where our function was negative, the reciprocal is also negative. This doesn't have a max or min, so its reciprocal doesn't either. And note that the reciprocal has horizontal asymptote y equal to 0. As x goes on, this is going to get closer and closer to the x-axis, but never touch or cross. So now the reciprocal of a quadratic function. So this is a parabola. It has vertex down at 0, -4. It's the base or parent function shifted down 4. There's the vertex. This has zeros or x-intercepts at 2 and -2, right? 2 squared take away 4 is 0, and -2 squared take away 4 is 0. So there's the vertex, and there are the zeros, and we know that it's opening up because it hasn't been flipped. There's no negative in front of the x squared. Let's go through our properties. The zeros become vertical asymptotes. The reciprocal graph always has horizontal asymptote on the x-axis, or y equals 0. Where this graph is positive above the x-axis, the reciprocal is positive. Over here as well, positive, positive, and where it's negative, the reciprocal is negative. Where my graph is decreasing, the reciprocal is increasing, decreasing, increasing, increasing, decreasing, increasing, decreasing. And finally, the minimum that we had here down at -4 turned into a maximum at the reciprocal value -1/4. Now let's take a look at rational functions of the form f of x over g of x, where each of these is a polynomial. So we're going to do a polynomial divided by some other polynomial. In order to sketch it, we're going to want to find the properties of the graph. First one is the zeros or x-intercepts. A rational function will have zeros where the numerator is equal to 0. So to find the zeros of a function, set the numerator equal to 0, and solve for x. Next, to get a y-intercept, no different than any other function, set x equals to 0 and solve for y. Now some new properties. Holes. A hole occurs on a graph when you're able to factor out some common factor in a rational function. An example will make this clearer, but we will get a hole at some value if the factor cancels out from the top and the bottom. Next, vertical asymptotes. Those occur anywhere the denominator equals to 0 after you've simplified. So you may get a hole, and if you cancel it out, it's not a vertical asymptote, but a hole. Whatever you do not cancel out in the denominator is a vertical asymptote. And lastly, the trickiest one, a horizontal asymptote. What we're going to do to find a horizontal asymptote is evaluate our function for very large values of x. Another way of thinking of the horizontal asymptote is the end behavior. It's what happens as x gets very large in both directions. Again, an example will make that clearer. So here I have some rational function, x squared minus 9 over x plus 3. So first we simplify. That numerator is factorable. It's a difference of squares. It factors into x plus 3 times x minus 3. Here you can see that we are going to get a whole. You can cancel out the common factor from the numerator and the denominator, and this function simplifies to this simple linear equation x minus 3. But remember, we still have this restriction. Just because the factor canceled doesn't mean that x can be -3. We still have a restriction there so that the denominator never equals to 0. But again, we canceled it, which means it's a whole. This is just a line with y-intercept at -3 and slope of 1. There it is. But if you look over here, where x equals to -3, where we said there's a restriction, we get a whole. So the graph is a normal line, except when we reach -3, it just hops over that one little point and continues onward. So now neither of these are factorable. Can't pull anything out here, can't pull anything out there. They have nothing in common, which means this graph will have no holes. Nothing cancels out. So let's go through the properties. To get my zeros or x-intercepts, I set the numerator to 0. When does 2x minus 9 equal to 0? Solving that, I get 9 over 2, or 4.5. Next, we can get a y-intercept. Y-intercepts occur when x is equal to 0. Setting x to 0 in my function, I get -9 over 3, or -3. Now the asymptotes. Vertical asymptotes occur when the denominator equals to 0. So setting the denominator to 0, I find I have a restriction at -3, and that restriction will be an asymptote. And now this tricky one, the horizontal asymptote. An easy way to find it is to simply plug in a large value of x. See what's happening as x is getting very, very big. I plugged in 1,000, just to get an idea. If you simplify this, the numerator will be some number just below 2,000. 2,000 take away 9. And the denominator will be some number just larger than 1,000. The larger that you plug in this value, the bigger the number is, the closer your number will be to 2. You may get 1.999 or perhaps 2.001. You're going to get values very close to 2. So we conclude that the horizontal asymptote is 2. As x gets bigger and bigger, my function is tending to the value 2. Putting this all together, there's my vertical asymptote at x equals -3, my horizontal asymptote at y equals to 2, my y-intercept at -3, my x-intercept at 4.5. Now remember, the definition of an asymptote is a line that your function gets closer and closer to, but never touches or crosses. So now I can piece together this segment of my graph. I know it has to pass through the intercepts and tend toward the asymptotes. If this kept going on, it would be getting closer and closer to the asymptote. There's another section to this graph just to the left of -3. It's going to be up here. If you're not entirely sure where the graph is going to be, we can always just find some accuracy point, just plug in a value for x and figure out whether it's going to be above the asymptote or below the asymptote. We could try plugging in, say, -4. If you did that, you'd find that you're up in the positives, which means your function is positive and tending toward infinity that way, and then down toward 2 that way. Solving rational equations. Remember, the nice thing about equations is as long as you do the same thing to each and every term, to both sides of the equal sign, the equation stays balanced. So because nobody seems to like working with fractions, we can just get rid of them when we have fractions in an equation. So if you notice, the denominator here is 2, 4, 4. The lowest common denominator of those numbers is, of course, 4. Multiplying each of these terms by 4 down here results in 4x over 2 minus 12x over 4 and 28 over 4. Now each of these, if you simplify, simply becomes 2x and a 3x and a 7, and just like that, fractions are gone, much easier to solve. Now I just collect my like terms, and finally we get x equals -7. This one's a bit trickier because our variable is in the denominator. So if I look at each of the denominators, x, x plus 1, and technically that's 2 over 1, the lowest common denominator is simply multiplying these two together. It's the best I can do. So we're going to take this entire equation and multiply everything by x and by x plus 1. The result is on this next line. This first thing is going to become 3 times x plus 1, still over x. The second one becomes 4 times x plus 1, still over x plus 1. And don't forget, the 2 also gets multiplied by x and by x plus 1. Now, there are common factors in the numerator and the denominator. Here the x's cancel out. Here the x plus 1 cancel out. Fractions are gone. Now that the fractions are gone, we treat this like any other equation. We want to distribute on this side, collect the like terms. This is quadratic, so we want all the terms on one side equal to 0. And now I factored, multiply to -6, add to -5, -6 and 1, and so on. Here it is in factored form, and I get two solutions, x equals 3 and x equals to -1/2. Unfortunately, rational inequalities are a lot more complicated. If you remember way back when we did linear inequalities, the rule was if you multiply or divide both sides by a negative value, the inequality symbol flips. When we're dealing with unknowns, we can't just multiply both sides because we don't know when it's positive and when it's negative. We don't know whether we should swap the inequality symbol. So for that reason, the best we can do is simplify this. I'm going to bring this rational over to the left-hand side. Now, in order to bring these two fractions together, I need a common denominator. These two multiplied together. So if I want to multiply this over here, I've also got to multiply the numerator. So there it is. I've taken that rational, multiplied top and bottom by x minus 3. Same over here. If I want this over there, I've got to multiply top and bottom by x plus 1. Now that I have a common denominator, I can subtract the numerators, this, subtract this, distribute everything out, collect like terms. If you do that, the numerator simplifies simply to x minus 7. So now this problem simplifies to when is this rational function greater than or equal to 0? When is it positive and when does it equal 0? The equality part is pretty easy to answer. At 7, when I put 7 up here, 7 minus 7 is 0, and over whatever the denominator may be is still 0. But when is it positive? When is it greater than 0? You have two options. Just like with polynomial inequalities, we sketched the graph to figure out when it's above the x-axis and when it's below the x-axis. You could sketch it. Alternately, you can make a sign chart. This graph, if we were to graph it, has an x-intercept at 7, and vertical asymptotes at -1 and +3, the values that make the denominator 0. The only way a function can swap from being positive to negative or negative to positive is if it passes through a 0 or it sort of hops over the asymptote. On one side of the asymptote, it's positive, and then on the other side of the asymptote, it may be negative. So we're going to test when this function is positive and when this function is negative using the 0 and the 2 values for the vertical asymptotes. So I've made this chart with 4 intervals before my first vertical asymptote, between my vertical asymptotes, between a vertical asymptote and 0, and finally after my 0. Those are all the spots where it can swap from positive to negative and negative to positive. To simplify this, I've put each of the factors here, Now I want to figure out when x is less than -1, are each of these factors positive or negative? Well, we can just select a number, say -2. If I put -2 into each of these, this would be -9, so it's negative. We don't actually care about the value, just whether it's positive or negative. If I put -2 in here, it would also be negative, -1. And if I put -2 in here, it would be -5. So all three of the factors would be negative, and therefore when I multiply these and divide this by that, you would get some negative number, regardless of which value of x you chose. Next, we want to test some value between -1 and 3. 0 is very easy. If I put 0 in here, that will be negative. 0 in for x here, that will be positive, +1. 0 in for x here, that will be -3. A negative divided by a positive and a negative multiplied ends up in a positive, right? This would be a negative over a negative. Moving on to some value between 3 and 7, say 4. This would be -3. This would be positive, and that would also be positive. Once again, this is the numerator. You divide it by the denominator. If you did so, the final answer would be negative. And finally, the last interval, some number greater than 7, 8, positive, positive, 8 minus 3, +5. All of these would be positive if we selected some value greater than 7. Multiplying these, dividing these, the final answer would be positive. So back to the question, which was, when is this function greater than or equal to 0? Well, greater than 0 means positive. So right here and right here, those are two intervals where it's positive. And so my final answer is, as long as x is between -1 and 3, and x is greater than or equal to 7. Remember we said the 0 is also a solution because we also want to know when it's equal to 0.